In this video, we're going to solve two other LP practice questions, question number 16 and 17, that are on transportation planning optimization. So I have the question here. We want to minimize the transportation cost. It's a cost minimization problem. And we want to know how much product to ship from each one of our suppliers to each one of our customers. So we know exactly the transportation cost per unit from each one of these routes. And we also know how much supply we have, the total supply available from, by each one of our suppliers, and also the total demand by each one of these customers. And these are just the name of the cities, right? The US cities representing suppliers and customers or buyers. And then in the next part, we're trying to see if we can find an alternative optimal solution using the procedures that we already know, the procedure that forces the zero decision variables to take positive values, while at the same time, we're trying to keep objective function equal to the optimal value that we find in the original problem. So let's first focus on question 16, and then we're going to look for an alternative optimal solution. So let me just go ahead and write down the decision variables. So decisions simply, decisions that we have to make would be how much of the product or how many units of the product to be shipped from each one of our suppliers to each one of our customers or each one of our buyers. We have 2 suppliers and 3 buyers. So in total, there's going to be 6 routes, potential routes that we can send, that we can ship product through. And we need to know how many units that is going to be shipped through each one of these routes. So decisions, how many units of product to be shipped from supplier I to buyer J. And I'm going to call this Xij. Xij, the amount of product shipped from supplier I to buyer J. So that would be my decision, which is basically the distribution plan that we're looking for. The objective would be to the cost, the total transportation cost. Total transportation cost that we want to minimize. Let me just add it here. We want to minimize the total transportation cost, which would be equals to 14 is the dollar amount that you have to pay for each unit of item that you sell, that you ship from Jefferson City to Des Moines, right? So it's going to be 14 times X11 plus 16 times X12, the amount shipped from Jefferson City to Kansas City, times 16, the per unit dollar amount that you have to pay, plus 7 X13 plus 8 X21 plus 10 X22 plus 5 X23. All right, so 14, 16, 7, 8, 10, and 5. All right, so that's for objective function. Next, subject to we have supply constraints and we have demand constraints. This is a minimization problem, and as you can see here, the total supply available will be 50. Some of these, the supply of these two cities, 30 plus 20, 50. And then at the other side also, we have, the sum of demands here, if you add them up, you will get 50 units. So 50 units available to supply, 50 units are asked by the buyers. So we have a match of supply and demand. But in general, in these type of questions where you're trying to minimize the cost, you want to make sure that you don't end up with zeros, because you want to make sure that to form your constraints in a way to make sure that you're shipping something, right? And because of that, usually you have to have less than or equal signs for your suppliers. For your supply, you can't go beyond 30. If you don't have more than 30, you can't sell more than 30. You can't ship more than 30. And for the buyers, usually this is where you get to force the decision variables to take positive, because here you can say if usually, and that's usually the case, demand is less than supply, you can force the amount shipped to this to be greater than or equal to 25. And that way you can make sure to get positive values for your decision variables. But in this specific example, we have a match of supply and demand, and it really doesn't matter. Even if you put equality, that's going to work out, and that's going to give you an optimal solution at the end of the day. Okay, so the constraints, we have supply constraints and we have demand constraints, the typical supply and demand constraints. So for the suppliers, we have X, the total amount shipped from the first supplier, Jefferson City, X1, 1 plus X1, 2 plus X1, 3. I can go, all the units that are shipped from this one should be less than or equal to 30 units. All right, so that's for the first one. And then for the second one, again, same thing, X21, X22, X3, X23 should be X21, X22, X23. Some of those should be less than or equal to 20. So that's the supply constraints. And then we have similar constraints, but this time for the buyers. So demand constraints, and then one for each one of them. So Des Moines, Kansas City, and St. Louis. So I'm gonna bring them up. I just copied and I'm gonna transpose. So now the total amount shipped to the first buyer should be greater than or equal to 20. So X1, 1 plus X2, 1, it can come from supplier 1 or supplier 2. That should be greater than or equal to 25. Like I said, you can put equality here as well. It's not going to change anything. So basically, if you put equality, you're saying that I want to make sure to send the right amount. But since the objective function is the minimization, it'll make sure not to send any unnecessary stuff, any unnecessary item to any of your buyers. So it'll make sure to make them binding actually at the end of the day. So X1, 2 plus X2, 2 greater than or equal to 15, which is the demand for the second buyer. For the third buyer, we have X 1, 3 plus X 2, 3 greater than or equal to 10. So that's just the demand constraint, the typical demand constraints. And then we have the non-negativity, which simply says Xij's cannot be negative. You can't, the amount that you ship from from an origin, from a supplier to another buyer cannot be negative by definition. All right. So I think we have the formulation. The formulation is ready. So I already typed these parameters that we're going to need for solving this problem. So that is just our formulation. Let me go ahead and develop the spreadsheet model. So we need to first develop the decision variables. Let me just come here. Decision variables. And then decision variables are going to be one per each route. All right. So this will be the amount shipped from the supplier to the buyer, right? And that would be blank. So these are my decision variables, 6 of them, all right? So decision variables, objective function would be, or you know what, objective, I just put it here, objective equals cost, and that would be the sum product of the decision variables with the transportation cost, comma, the transportation cost, so that would be the objective function. And then we have these demand and supply constraints. So the total amount shipped from each city. So let me just write it here, shipped from, shipped to. The total amount shipped from each city would be sum of the amount shipped to buyer 1, buyer 2, and buyer 3. All right. And same thing for supplier number 2. The total amount shipped from that would be equal to the sum of the amount shipped to buyer 1, buyer 2, buyer 3. All right, so shipped from this, let me just come here. So the supply constraints, the amount shipped from each one of these suppliers should be less than or equal to their capacity. And their capacity would be 30 for Jefferson City and 20 for Omaha. So we have to make sure to respect that. We have to make sure not to violate the supply capacity or supply constraint, right? The total amount shipped from each supplier should be less than or equal to the capacity of that supplier. The total amount shipped to each buyer would be the sum of these two values, because let's say buyer 1 can get its product from supplier 1 or supplier 2, and the sum of these two will make up the total amount that the buyer 1 has received. So that should be greater than or equal to 25, and 25 is here. sorry, equal 25. And I can just drag it to the right. If you just set it up right, you can actually enjoy being able to drag it to the right or the left, right? So you being able to copy and paste the formula. So, all right, so this is the demand constraints. The total amount shipped to each one of them should be greater than or equal to the amount that they've asked for. All right, so I think we have everything. We have the decision variables, 6 of them. We have the objective function, which is the total transportation cost that we want to minimize. And we have 2 supply constraints, 3 demand constraints or buyer-related constraints. So let me go ahead and go to Solver Data tab. Solver. We want to minimize, make sure to check minimize the objective function, the total cost, by changing these 6 variables subject to the total amount shipped from each supplier less than or equal to the maximum amount available, the total amount shipped to each customer greater than or equal to the amount that they requested, okay? And then make sure to change the solving method to simplex LP. And I think we are good to go. Solve it, and again, Excel found a solution, an optimal solution. Let's take a look. The minimum transportation cost would be $540 if you want to satisfy the demand of our buyers using the supply capacity of our suppliers. And this is how you do it. This is basically how you can satisfy the buyers using the capacity. All right, all of these constraints are binding. As you can see, all these 5 constraints are binding, and we call a constraint binding where the value of the left hand side is equal to the value of right hand side at the optimality after you solve it, right? So yeah, so that would be the answer to question number 16. Now we need to look at the possibility for an alternative optimal solution. What I'm going to do now, I'm going to go ahead and create, I'm going to create another sheet. I'm going to copy this sheet, paste it, and I'm going to rename it to 17, question 17. So move or copy this. So click here, move or copy, create a copy. Let's say move it to the end. Okay. And I'm going to call this one question 17. And I'm going to call this one question 16. So on question 17, let's just go back and make the necessary changes to our formulation and our spreadsheet model. So this is an alternative search type of model that we are generating, alternative search. All right. So in the alternative search, the decisions are the same. The objective is not anymore the total transportation cost. The previous objective function would become a new constraint. So I'll copy this. The total transportation cost will become a new constraints, cost constraints. And that would be, let me maybe add one more cell here, one more row here. Constraint, yeah, maybe another one. Let's just put it right here. So the total transportation cost should be, I'm looking for another alternative solution, and I want to make sure that my transportation cost, or my cost, simply stays at the optimal level equals 540. So I want my cost. How do I know 540? Because I found that the best cost, the best distribution plan that I can have will lead to the minimum transportation cost of 540. It's impossible to come up with a distribution plan that leads to a smaller cost than this one. And if you want your new solution to be as good as your first one, you want to make sure the cost to stay at the same level, 540. But then how about the objective function? So if we just change that to a constraint, what happens to our objective function? Objective function will become now maximum of sum of zeros in original solution. Sum of zeros, I mean 0 DVs, decision variables. All the decision variables that took 0 in the optimal solution in the original problem that we have it here. You see this one and this one, x2, 2 and x2, 3. That's how we call them in our formulation. x2, 2 plus x2, 3. So those are the ones that I want to force them to take positive values, right? So because these are zeros, and we are hoping that by changing this to a maximization of these two, some of these two variables, at least one of them take positive. And if they take a positive value, it means that we have found an alternative solution while keeping the total cost at the optimal level of 540. So now I come here, objective cost, I'm just going to change this to cost constraint. So the cost function, I want it to be equal to, I type now, this time I type 540. I typed 540, right? I want it to be, this is my new constraints, cost constraints. The cost function using the decision variables to stay at 540. Now the new objective function that I want to maximize would be the sum of these two guys, x22 plus x23, right? And it's the alternative search objective function. So objective function for the model that is used for finding the alternative optimal solution. So now that I have the objective function, I can go ahead and go to the data tab and call the solver and go ahead and solve the alternative search model. So this time we want to maximize the new objective function maximize the new objective function. Decision variables are the same. The constraints are the same. The only thing would be to add the cost constraint. And that would be left-hand side exactly equal to 540. Okay. So everything is, looks great. I just go ahead and solve it. And we're hoping for objective function to take a positive value. Let's see if that is the case. So again, I'm not looking for anything specific in the answer or sensitivity report. So, okay. We just found an alternative solution, guys. So if this solution, if the objective function is 15, if it's positive, it means that this is different from my original. And the cost is staying at the same level, 540. So this is 0. And when I compare this with the original answer, 20 and 10, let's see. I had 20 and 10. So this is obviously different, but with the same transportation cost, minimum transportation cost level of 540.